Uh, hi, hi everyone. Today we are presenting our group presentation for. These are our teammates Kalyan, Harishankar, and I'm Jaydeep. Today we are discussing the topic about learning real-time A-star path planner for unmanned air vehicle targeting sensing. Abstract. Like this paper is mostly focusing on the real-time path planning for unmanned air vehicle like targeting target sensing where in which they have used A star path algorithm for sensing closely s- spaced targets. Like this paper shows how to get the optimal shortest path for an unmanned air vehicle by using the A star shortest path techniques. They are finding the path for UAV to closely spaced targets. The result of the path planning is to produce shortest distance path in acceptable short running time. Like the running time and path length performance of the parsec is directly influenced by the parameter of LRTSR algorithms. Introduction. Path planning is the essential activity of the autonomous vehicles. The problem of focusing for this work is to develop a path for a group of target which are closely spaced targets and utilize the sensor footprints. A path planning is particularly difficult because of the dynamic limitations of the aircraft. In this figure one, there is a motion sensor which shows the footprints to reach three targets. Based on the path provided by the sensor footprints, the UAV has to reach all the targets by the optimal multi multi-target path. The three targets need to be reached by the UAV that shows includes the path segments from one target to another target, and also we need to take in consideration of dynamic limitations of the aircraft. Using the A-star algorithm, the shortest path need to be given by reaching all the targets. The minimum turn radius of the aircraft should be taken care to reach the all the targets. Like by taking all into consideration, there are two ways to plan the path to reach in all the directions. As discussed in the above slide, we need to take all the mentioned points into consideration and reach all the three targets. As shown in the figure 2, a point-to-point optimal path plan, optimal multi-target path plan. By considering these two paths, in the best path plan, the path segment from the starting place to the target clearly begins the best. Like in the 5002, and this will be going to these targets 1, 2, and 3. This path can also be referred to as a multi-target paths, where the vehicle will examine future targets, resulting in the shortest path length possible for viewing all of them. There are a lot of pathways that starting from the target of their interests. When it comes to the sensing targets in close proximity to view order, the problem is knowing when to do it. It is know like when to get the target by target. Effective path planning approaches for viewing close targets of UAV require the following capabilities, like overcomes the effect of uh, coupling between two sensing paths to plan optical or non-optical paths through nervous goals, enormous goals. Discrete discrete short discrete step paths. A successful path planning algorithm should satisfy all the dynamic constraints in the vehicle. The choice of which of these all these each steps is motivated by a set of objects for the phase rather than getting from point A to point B. Sensing a set of targets in each, like given in the example, like figure 3 and figure 4. Normalizing by DS minimum targets radius RT gives the vehicle maximum heading chances, like uh, by going to each steps. Like as shown in the figure 3, there are multiple nodes where there is a parent node A and the following nodes by all chain nodes, like from up to C. Like as shown, each node has the parent and was denoted by the set of S. As the node in the tree increases, the depth will also be increased. Uh,
Hi, I'm Kalyan. I have to explain about the learning real-time A-star algorithm. The A-star algorithm is typically chosen for path planning problems in grid-based worlds. This can be used in the real-world examples like grid-based research, tree search, direct graph, or other. The LRT A-star algorithm is chosen over the A-star algorithm because uh, it has a limiting factor on the performance of the path planner, but the memory space required to store the expanded nodes, it chooses the less memory space. uh, the algorithm details: the LRT algorithm is simple and intelligent, and each node has a heuristic value till the end. For each step of the search, the heuristic value of the present node will change, and it gets better. At this point, the search has learned the minimum length path that accomplishes the desired objectives. When the actual path length for the root node, then the search has found the optimal path. Initial heuristic: the basic requirement for the LRT A star algorithm is HI should be less than or equal to HI star, so that the each node can be executed. If the node on the optimal path exceeds or over the distance to the goal, then the search may move to that node, or it is not the optimal path. And the calculation of appropriate initial value of these heuristics is essential to the performance of the LRT A star search. So that heuristics in the LRT A star research problems are estimates of the distance that must be traveled from the current node to complete the remaining task. And the easy way to calculate the heuristics is to use the distance to the longest target as the initial heuristic value, so that we know that the vehicle must travel at least that far to complete its objectives. In the initial heuristic values, it can be guaranteed and accepted when it is close to the actual path length, and the search may be slowed down. uh, the process can be continued till we find the best path to reach the goal node. And there are some termination conditions that we use the methods to terminate the tree directly, like by trimming the tree, or by pruning it. There are two extreme conditions, in which one extreme is that the search runs until the heuristic change is zero, which guarantees that the minimum length path has been found, but possibly requires a significant amount of runtime. On the other extreme, the search runs until a maximum running time is reached. These two extremes may be combined to create a terminating conditions, which can improve the path length. and it provides the ability to terminate the algorithm and branching terminals to get the best result from the LRT star search. Memory management and path tree pruning are required. Uh, Here we compare, we test and compare between the LRT A-star and uh, NILRT A-star algorithms. The test can be conducted on 2000 different target scenarios. But there is an advantage for the LRT A-star tree search, that which is made between the path generated by the LRT A-star algorithm and path found through a brute force global search based on Dubin's path, in which the size of the sensor footprint for the LRT A-star algorithm was reduced to approximate the vehicle passing through the target points. The path length performance for these two algorithms at the different step sizes is given that the mean path length increases approximately 19% over the range of step sizes, indicating that the smaller step sizes are better. The increase in the mean path between it can be happen between 0.2 and 0.4 radians, uh, so that we choose the radians value between 0.2 and 0.4, and we can increase the radians value by 0.05. And the running times of these LRT A-star and NILRT A-star algorithms. The running time data in a platform it can be based on an independent fashion. The running time is not same as the number of nodes from the path tree that are expanded, but is the total number of moves made from node to node during the tree search. The average total running times for both algorithms at the various step sizes, which is shown in the graph, and the average running time for the LRT A-star algorithm is about 8 lakh nodes and about 1,50,000 nodes for the NILRT A-star algorithm. At a step size of 0.3 radians, the mean running time for the LRT A-star algorithm drops at about 2 lakhs nodes, which the drop rate is almost like about 98%. And as the step size continue to increase, the mean running time decreases further uh, for both the nodes. And we choose the different number of target scenarios to test this algorithm's performance. Like we choose like 2000 random target scenarios for each target node between 1 and 8, with a step size for the test are 0.25 radians. The, in conclusion, I state that the shortest paths are always generated by the LRT A-star algorithm, but which takes longer time when compared to that of the NILRT A-star algorithm. But the NILRT A-star method succeeds in sacrificing some path length performances. Both the algorithms establish the best viewing order and make full use of the sensor footprints to view the targets. They also determine the optimal viewing order as part of the planning process. From here, my friend Harishankar will explain.
Thank you, Jaydeep. Thank you, Kalyan. So I am Harishankar Prasad. So I'm continuing with the topic KNN LRTA star simple subgoaling for real-time search. So let me start with the introduction. So the real-time heuristic function satisfies irrespective of the problem size. So here we are using this function to solve the problems in video gaming. So actually the problems will be lying between to find the distance between two nodes. So there the agent must be able to think and make decisions over like which path to be selected. or which move to be selected. So based on the situations, the scaling of the problem will be generally varying from small to big. So for example, it is a complex solution. So the agent must be trying to make decision based on the complexity of the problem. So this type of implementation will be useful in video games that uses artificial intelligence control that reacts. And for example, I'm giving a command. So based on the command, the agent must be capturing what commands he is taking, and he must respond based on the commands. So the actions are purely dependent on the user commands. So in AI control games, we can observe that there are many commands given by the user at particular time. So that like these actions are very faster. So we need to respond in very less time. If the agent taking more time to give response, so automatically the person loses interest in the game. So the algorithm must perform in such a way that in a particular period of time, it must take decisions very fastly and respond to the user. So one of the most important realities is to prepare plan repeatedly. For example, the moves may not be one time or two times. So it will be continued throughout the game. So whenever the person is giving some commands, so at particular instance of time, the agent must be thinking what to make the next path. So this step must be repeatedly until the game is completed. So there are so common problems that video game has is searching path between two locations. When we take between a chess, so automatically he needs to know, the agent must know what step need to be taken to provide a counter to the other person outside the screen. So there are different types of algorithms. Before this, there are static algorithms. We use static algorithms as A star, IDA star, PRA star. So replanning algorithms are D star. So anytime algorithms are ARA star. Anytime replanning algorithm AD star. So these are different algorithms. So when we are going for DLRTA star, so the idea was first implemented to implement the real heuristic search algorithm. So this was used to analyze the to use the space and computes a database of subgoals. So here subgoals are created in a database. So based on the subgoals, it is going to use the algorithm is going to use in making the decisions. So it has a substantial memory. That means it is having some 70 more times than a normal algorithm works, and have a complex pre-processing modules. So it is like it is performing some operations like at a complex level. So it is a non-trivial code, like it will be having some Dijkstra algorithm at initial stages. So this will help to react abstract goal and help in tracing the path for the algorithm. So here we can see the picture. The subgoals are defined with KNN LRTA star, and this figure 2 is LRTA star at runtime. So basically, see the S goal is coming in this path. So after coming this, it needs to find the path. So here there is a break. So the path is going to S dash star. So then at runtime, it will be finding some closest goal. So closest data entry, it is going to find here. So these two marks indicating that heuristic distances between agent situations. So it is very close to S dash start and S start. So we are going for run search. So computing a subgoal for every state of pair is somewhat difficult for non-triple mapping. So where most of the agent states and goals not be same. For example, if agent wants to have some particular goal, it may not be in the database. So we cannot wait till it is created. So this agent will be taking the similar type of goal or the nearest one it is searching for. Like it will not exactly find the solution what it requires, but it will be owning the state which is readily available for it. So one of the common thing algorithm we use is k nearest neighbors. So in this algorithm, they are going to use this because it will help in finding the nearest goal which is present in the database. So let me continue with the properties. So for particular time, when we take for KNN LRTA to compute goals, the algorithm will be running either KNN LRTA star or the goals. The fact is that when we go for n-sized databases, so databases size may be some different. So we are considering it as an n size. So they will be having some different map sizes and they need to mapping. So for that particular reason, the algorithm should perform hill climbing limited by m. So when when it performs the mappings for that particular n and m, so there are the worst case time periods. So these are mentioned here. So the worst case is big O of mn. So based on that, it is having some worst case. When we go for the asymptotic notation for the memory complexity is big O of n. So where sub goal database is having also same as memory complexity, that is big O of n. Whereas LRTA star is having a big O of n. So when it comes to the worst case of the agent, it consumes not more than a big O of n plus v. So when we are going for empirical evaluation, we have compared 8 games. These are the mappings of 8 games. Okay. We have taken from 2 different games. So it will be having some different dimensions. The first 5 are taken from Baldur's Gate. So the rest 3 are taken from the video game called Warcraft 3. So these mappings will be having different dimensions that are different dimensions. Okay, that will be ranging from 150 into 141 to 234 into 274. So let me conclude this topic. The primary purpose of this paper is to develop the high performance search algorithm that is used to solve the problems in gaming field. So in order to create a more interest in gaming, the algorithm should perform well and give high accurate value in choosing the steps. So like it's a relaxing memory of DLRTA. The new algorithm KNN LRTA is used to offer clear benefits for finding the path for application in video games. So like choosing, if we are choosing any path that is not suitable for the move, then automatically they will be losing some interest. So there are some of the future works we have included here. It is believed that KNN LRA star need to provide the full potential while implementing a runtime performances. So whenever selecting the goals at random, more intelligent ways should be created so that the algorithm chooses the best steps that will help in improving the accuracy. So thanking you, everyone.